Chapter 19: Electric Currents and Circuits. Let's talk about electric currents and define electric currents. We already discussed that electrons are light particles, they carry negative charge, and they can move inside conductors or inside a metal wire. So electrons can easily move through a wire. This motion of electron through a wire is related to the concept called electric current. To find the magnitude of this current, we need to divide amount of charge that moves along the wire by delta T, like here, delta Q over delta T. What's important to understand here, and don't confuse it, this delta Q in a definition of current is a positive charge. Even though physically they don't go anywhere, physically electrons doing all the motion and they are negative. So current is defined as a positive current always goes in a direction opposite to electron motion. This has happened from historical reasons and we just have to accept it. Electrons doing all the motion, so if you have analogy with water, with river flow, electrons are flowing, creating electrical current, but the positive direction of the current goes to opposite direction. Electric current is defined in terms of net positive charge flow. Historical reason, nothing you can do about it. What's also important here? Units. Current is measured in amperes, special name, named after Andrew Marie Ampere, this guy over here. Here's his picture. It's also defined as 1 coulomb per second. Makes sense. Definition of current: I is equal delta Q over delta T. Q is measured in coulombs. Time is measured second. So 1 ampere is equal 1 coulomb per second. Delta Q over delta T. In the standard system of units, the ampere is a primary unit, and coulomb and volt, for example, are defined in terms of the ampere. This is just an interesting fact. Movement of charges. The definition of current uses the net charge, delta Q, that passes a particular point during a fixed time interval, delta T. Current is equal delta Q over delta T. Wires are not the only material that can have a current running through it. Current can go through air, through water, through human body, and through pretty much any conducting material. The amount of charge, delta Q, can be a result of many possible configurations. For example, sometimes we can have a few particles with a very large charge. That's going to create a large current because we have a few particles moving with a very large charge. It's just being created this way. We can have many particles positively or negatively charged with a small charge, so we'll create the same amount of big current. We can also have a combination of positive and negative charges. So think about this way: we have electrons going this way, and we have one positively charged proton going this way. So we're going to have a current in this situation equal 1 electron per this amount of time. If we would not have this proton, or we can have another positively charged electron to the flow, we're going to have a larger current. Or if we can have lots of more protons going this way, then you're going to have no current at all actually in this situation. Let's add another guy. Here's a proton. It has this way. So this is like a general case. You should realize that current, even though defined as a motion of positive net charge, could be created by motion of negative charged particles, positively charged particles. As soon as the charge moving somewhere, we have electrical current. If the current is carried by positive charges moving with a given velocity, the direction of the current is parallel to this velocity. On the other side, you have to remember that if a current is carried by negative charges, the direction of the current is opposite to the charge's velocity. This is a small summary. A positive electric current can be produced by positive charges moving in one direction, negative charges moving in the opposite direction. Current in the metal is carried by electrons, so it goes in the opposite direction of the electron motion. In a liquid or gas, the current is generally carried by a combination of positive ions moving in one direction and a negative ions moving in the opposite direction. So then we have to find a net charge motion in a fixed direction and divided by unit of time. This is like how we can have a current in gas or liquid. Let's solve problem 2 from a textbook. As a treatment for chronic back pain, a medical patient may be fitted with a device that passes a small electric current, 10 milliamperes, through the muscles in the lower back, as shown in the figure. If the current is supplied in short pulses, half second in length, how many electrons pass through the muscles during one pulse? Okay, let's make it tiny, put it up here that I can write next to it. Okay, so what do we have? We know that, okay, what's given? Current is 10 milliamps. Delta T, time of one pulse, is 0.5 second. We're looking for number of electron during this pulse. By definition of current, current is equal delta Q over delta T. Charge, delta Q, always proportional to the charge of one electron, multiplied by number of electrons that are in that charge. So we can combine those two equations and solve for number of electrons. So delta Q is equal I times delta T, or electrons, number of electrons is equal I delta T. So number of electrons is equal I delta T divided by E. Let's plug in numbers, and E then is equal 10 times 10 to the negative 3 amperes times 0.5 seconds divided by 1.6, 10 to the negative 19 coulombs. So we can plug it in the calculators and get this number, 3.1, 10 to the positive 16 electrons. Okay, this is our answer. Number of electrons passing through the pulse is 3.1, 10 to the power of 16. Okay, so what does it mean? That it's a huge number of electrons, first of all. But if you look at the mole value, you know from chemistry, so it's less than 1 millionth of mole of electrons pass through the muscles in half second. So if you want to do physical therapy, that's one of the problem you might need to solve in one of your exams. Let's solve another problem, problem 5. During thunderstorm, lightning bolt carries current between a cloud and the ground below. If a particular bolt carries a total charge of 20 coulombs in 1 millisecond, what is the magnitude of the current? How many electrons are involved in this process? Okay, let's write down what's given again and look at the problem. Given total charge delta Q is equal 20 coulombs. Delta T is now 1 × 10⁻³ seconds. Let's convert milliseconds to seconds right away. We are looking for magnitude of a current and how many electrons are involved in a process. So to solve this problem, we need the same two formulas: definition of current, delta Q over delta T, and delta Q is equal charge of one electron by number of electrons we have in this delta Q. So identical two formulas as in the previous problem. Should be easy. So then current is equal 20 coulombs over 1 × 10⁻³ seconds. That's going to give us 2 × 10⁴ amperes. This is your first answer. And a number of electron would be equal delta Q over E. This is charge of one electron, 20 coulombs divided by 1.6 10⁻⁹ coulombs. It's going to be 1.3 10⁻20 electrons. Okay. So first, what we should realize in this problem, this current, 20 kiloamps, is incredibly high current. That can kill you. We don't really have that many electrons if you compare to the previous problem. Well, it is bigger, but it's not. What's crucial here is that the time is very short. The time is 1 millisecond. That's why the current is so large, pretty much because it lasts such a short time. This will conclude the first part of this lecture.